from Marek Beer. I'm standing in here for Marek Beer, the head of the graduate school or research training group MIP. And we will welcome today Jürgen Jost, but before we go there, and I actually hand over to the student to do the job, I will just briefly explain what is this about. The Charlemagne Lecture, we're doing this for 15 years. It started with our graduate school ACES, and I actually remember that we wanted to do this kind of extra lecture and we were looking for a name. And my colleague Martin Frank, who's now in Karlsruhe, he suggested Charlemagne as a joke. And then it somehow stuck, and it was a joke because everything in Aachen is about Charlemagne, and we thought that this is actually the way to go. And it turned out to be actually a very nice name, and the people somehow remember this. And for 15 years we're doing this, and it's a special thing because part of the design is that we wanted to empower our graduate students to really do the whole job of contacting somehow big shots, really relevant people to the field, getting them convinced to come to Aachen and then basically give a talk here, do the discussion, go with them to dinner and so on. And we had very nice feedback from many very established high-level people. Oh, that's such a nice idea to interact with the students, to the extent that actually one even said he would not have come if it was not for the students. Yeah, so I think that this is a really nice thing. Thanks for being here. And with this, I hand over to the actual introduction by Prof.
Yeah, and it's a great pleasure to introduce our speaker of this year's Charlemagne Distinguished Lecture Series 2026. It's Professor Jürgen Jost, the Director of the Mathematik-Institut of the Sciences and Mathematics in Leipzig. And his contributions reach from geometric analysis, Riemannian geometry, dynamical systems, to a lot of other fields of mathematics, and most importantly, he has always applied these concepts to biology, physics, and other sciences. Differential geometry has come a long way ever since it has been introduced in its current form by Bernhard Riemann in 1854. And what makes today's lecture particularly exciting is that we take this century of accumulated knowledge and Professor Jost's geometric intuition to tackle the most pressing issue in today's data science problems. And today's talk is going to be about how geometry can illuminate dimensionality reduction and data visualization. And this is exactly the kind of perspective we hope to bring to the Charlemagne Distinguished Lecture Series. We want to be at the cutting edge of research and be part of the avant-garde. And therefore, please join me in the name of the IRTG and in particular of all the students to welcome Professor Jürgen Jost for today's lecture.
Yeah, thank you very much for the kind invitation, and in particular to Fabian Konrad for organizing and arranging everything so well. Everything is going so smoothly and nicely. Of course, I enjoy the interaction with the students. So this is not my first time in Aachen. I came here for the first time when I was just a few months old. But then I left already when I was three years old. So that was my first period in Aachen. Since then, I've only been back every now and then. In fact, last time I was here last August for a workshop on network analysis. And it has always been a pleasure to return to Aachen for me. And so I enjoy being here with you and also being able to talk about some of my current research. I mean, we are doing many things, but this is perhaps one of the most exciting directions at this moment. Okay, so what is the problem? We are confronted, since whatever 20 years, with ever more and ever larger data sets from many domains. And of course, as scientists, we want to analyze, we want to interpret, and we want to understand them. Now, these data are not so easy because they come typically from elaborate technical devices like the astronomical observations that span a wide range of frequencies much beyond visible light, or the traces and collisions of subatomic particles, or by the most advanced physical imaging techniques that work in molecular biology. But so there's a problem there. These data are usually outside the range of our sensory experience. So we don't have an intuitive grasp on this data. And so they are difficult to handle. And in particular, since we don't have a direct intuition there, human psychology does not directly help us. I mean, traditionally, you look at the stars, you see something, you record it, you look at an animal, you analyze its bones or whatever, and you can understand what is happening. But with the current data, you can no longer do that so easily. And so therefore, we need mathematics. And of course, that is good for us as mathematicians. But of course, we need to deliver then something. But first of all, we need something. We need structure. So the data should have some structure. Of course, usually the data are not random. Otherwise, we couldn't say much. We could just say this is white noise, but that is not so insightful. But that is not the interesting aspect of it. We want to see what is there beyond and above the noise. And so the data should carry some structure. But how can we detect or guess such structure? We assume that there's some structure there, but we don't know which. But first of all, there are regularities, symmetries, invariances, correlations in the data. And so therefore, the data are intrinsically usually not as high-dimensional as they may appear. With all the measuring devices, you have many degrees of freedom, maybe a few hundred degrees of freedom. You record everything for every degree of freedom, so you have many data points, and then you put them naively into high-dimensional space. But that is not really the structure there. Even if you represent them in a 300-dimensional Euclidean or Cartesian space, that is not what really the structure of the data is. And that is what we want to find. And so we need mathematical methods that can exploit that intrinsically the data are regular and lower dimensional than they appear. And we then should represent them also in such a way, maybe even in lower dimensions than they actually naturally consist of, in order to bring out the essential features that are particular to the data that we are looking at. And ideally, we want to represent them in 2 dimensions or at most in 3 dimensions so that people can take a look. Yeah? And we want to represent them in such a way that the most prominent aspects of the structure become obvious or apparent in this low-dimensional representation. And more precisely, as geometers, we don't just assume that there's some structure, we assume that there's a metric structure. That is, we have distances between data points, dissimilarities or whatever that we can quantify that. This could be Euclidean distances, just take the square root of the squares of the sum of the squares of the difference of the individual measurements. Or that could be some whatever abstract inner distances. And so the algorithms then should extract features of the data from these metric relations, from these distance relations. So manifold learning is an established technique. So when the data are in some high-dimensional space, but they are assumed to lie or be concentrated in near some low-dimensional smooth submanifold that may stretch into many ambient directions. And this manifold should be recovered by sampling the data. So, of course, the manifold typically is not just a flat subspace, otherwise it would be trivial. It may be highly curved, it may stretch in different directions. Here we just have a surface in 3 space, but you could even have a curve in a 50-dimensional space that stretches in all dimensions. It can be locally approximated by its tangent space by something flat, but that doesn't really capture the geometry there. So that is one aspect on one hand. On the other hand, you could also use tools from network analysis. You would represent the data as graphs by connecting data points that are sufficiently close or that are sufficiently similar or that have a particular relation. And it could be even a quantitative graph structure, that is, the edges could have particular lengths that indicates the distances between the data points. And then we could use concepts from graph theory to identify particular features. So here you see a couple of graphs. So some graph here are the so-called complete graphs, where every point is connected with every other point. You have complete bipartite graphs where you have two classes of points, so that each point in one class is connected with all points in the other class, but not with any point in the same class. These are some typical graphs. Of course, data typically don't quite match that, but of course you want to have certain paradigms or comparison models, and that you can then say the data are similar maybe to a complete bipartite graph and then quantify the difference or so. Or you could represent them by hypergraphs. In a graph, only two elements always can stand in a relation. In a hypergraph, you could have more points that stand in a relation. And so here's a particular one that played some role in our research. This is so-called the hyperflower. Here you have a central group of vertices that not only stand in relation with each other, but that also stand in relation with all the other points. And then you have peripheral points, for example, these 3 points stand in relation with each other and with the central ones. You have a core periphery distinction here. And that is, for instance, important when you want to understand chemical reaction networks. Chemical substances react with each other, and typically you have a couple of educts and you have a couple of products, and this is not one educt and one product, a couple of educts and a couple of products, so you have hypergraph with even more structure. And then you want to analyze that. So for example, we are looking at the data set of all chemical substances reactions ever recorded in the chemical literature. So by now we have far more than 20 million known substances and more than 40 million known reactions. And then we analyze that and we mathematically represent that as a hypergraph, and we are looking what particular structure that hypergraph has. Another method is topological data analysis. So for each data point, you try to see which other data points can you capture in a net of radius r, which are at distance at most r from the data point in question. And then mathematically you have distance balls, and then you look to what extent these distance balls intersect for different points and for different radii, and how that intersection pattern changes when you vary the radius r. I will come back to that a little later, but you turn that into a combinatorial structure, into a so-called simplicial complex, and then compute its topological invariance, so-called homology classes, and then you look which homology classes persist for a large range of R, and then you say that these represent important features of the data. So now coming back to manifold learning. So in manifold learning, a graph is constructed by joining sufficiently close sample points. So we assume that we have the data, and maybe we sample the data from some underlying manifold which we don't really know. Yeah, but we make the assumption that the data sit on a low-dimensional manifold, and that is important because manifold, if the data are on a manifold, if you have a couple of data points, then you can interpolate between them because the manifold is smooth. if you would have a structure with singularities, that would not be so easy to capture, because the singularities are typically lower dimensional, and when you randomly sample points, then you wouldn't capture any singular structures. You could only indirectly infer it, but not directly by interpolation. So therefore, the manifold assumption is a useful assumption. But then, when we want to identify the manifold, we just have the data points. We have more and more data points. They get denser and denser, but you never have the full manifold. But then we construct a graph by connecting data points that are sufficiently close to each other, and then have more and more data points, and then look at a particular operator, the Laplace-Beltrami operator, or the Laplace-Beltrami operator of the graph, and then mathematically we show that this converges to a certain operator on the manifold. It's Laplace-Beltrami operator, with the help of which we can recover the manifold. That is, we have an operator, we look at its eigenfunctions and eigenvalues, and in the limit they tell us something about the underlying structure, the putative underlying structure. And likewise, network analysis can also use eigenvalues and eigenfunctions of such objects, and also so-called curvature statistics, and that provides some foundations of machine learning and data analysis. And in topological data analysis, you have the intersection patterns of the balls, and we can also relate them to curvature notions for metric spaces. All that will be explained in a little more detail later on, but that is already spanning some kind of mathematical directions and mathematical methods with which we can approach the data that we have. So here's an example. Of course, this is a toy example. This is a skeleton of a mammoth. Of course, now here we have something which we can already understand. That is not typical for the data that we are producing, but I just want to use that to illustrate it. Yeah? Of course, now you can easily recover the three-dimensional image, but that is not the point. The question is how to project the data onto 2 dimensions to make the different structures explicit if you're not able to reconstruct the 3-dimensional shape. So the point is you have the trunk of the body, and you have the different appendices, the legs, the tail, and the tusks. Because the trunk of the elephant doesn't contain bones, and so that is not visible here. So here's one method that represents it. I mean, it gets something because it separates the different appendices. Yeah? It's clearly not optimal, but somehow it goes in the direction that we want to have. Here's another method that also separates the different appendices in a different way, and here's our method, which I will explain in a moment, that from my perspective at least separates the different appendices most clearly. The tusks, the hind legs, and the tail, and the front legs. And that is somehow what you want to have, to get the structure in such a way that it becomes most explicit in a 2-dimensional representation without having recourse to anything in high dimensions. Okay, and so that is a method that we have developed, and now I want to explain to you some of the mathematics behind it, because I think that is quite nice. So again, our general aspects. The data are often given in some high dimensional space, typically but not necessarily a Euclidean space. They carry distances, metric relations. You have distances between data points, and they are supposed to possess some intrinsic regularities and correlations. That is, intrinsically they should be of much lower dimension than the ambient space in which they are presented. And so therefore we assume that they sit on some smooth lower dimensional manifold, and which is an assumption that allows for interpolation between data points, as I had already mentioned. But of course, recalling the picture that we saw earlier, this manifold need not be linear. It may be highly curved, and it may stretch into many ambient directions. And also the data need not be uniformly distributed on some manifolds. There may be denser spots and less dense spots. And in the end, we want to visualize the data in 2 dimensions or perhaps 3 dimensions, and by preserving the qualitative aspects, for example, the clusters in the data, as well as possible. So that is a situation that we are faced with, that is the task, that is our challenge. So there are some existing methods. Let me just give some names here. So Hinton, maybe you know, because he was awarded a Nobel Prize for his work in machine learning and artificial intelligence. But the most widely applied method, in particular biologists, currently is UMAP. So now, how do we go about this? As I already said, we connect data points that are sufficiently close to get a graph. And when more and more data points are sampled, the graphs get denser and should ultimately approximate a manifold. Now then, when we have these graphs, somehow we want to project them onto the plane. We want to approximate these graphs that of course sit in high dimensions by planar ones, in such a way that the essential features of the data manifold are preserved and become visible and even highlighted. Of course, this does not always work. So the properties of the data may only be apparent in high dimensions, and they may get lost by a projection into 2 dimensions. So we need to make some compromises. It will not be ideal, but this is the best that we try to find the best 2-dimensional projection that the people in the applications can then work with. So we have our graphs, but in order to improve that, we first need to pre-process and modify the graphs in order to amplify the local features, for instance, the clusters, before projecting them. So we're not just taking the graph as it is, we modify it first. So again, we connect each data point now with its k nearest neighbors, and of course that changes when we have more and more data points. Yeah, what are the k nearest neighbors of a point to get a collection of graphs, and for each point, then when we connect it with its k nearest neighbors, we just have a star graph. The point in question in the center, and then connections to the k nearest neighbors. So that is trivial. We then have these star graphs, and we will modify them in between. Then we have different star graphs, and then we need to bring them together again. We need to merge them. And therefore, for that, tools from category theory are used, but I will not go too much into the details here. And then the resulting space should be projected onto 2 dimensions with minimal distortion. That's a relatively simple program. But of course, carrying it out, as we will see, requires some mathematics. So, and here we come to Bernhard Riemann, who was mentioned already. And in fact, yesterday I was at a conference in Hanover, and I gave a talk about Bernhard Riemann because it's the bicentenary of his birth. So he was born 200 years ago in 1826. And there is currently a week-long conference in Hanover, but I left it already yesterday afternoon to come here. So let me then take the opportunity, nevertheless, to give you a brief introduction to Bernhard Riemann. So 1854, it was already mentioned in Fabian Conrad's introduction, was a decisive date. And in fact, it was the 10th of June. And that was an important date, and let me maybe tell you some story how it came about. So Riemann, of course, was a very talented and gifted mathematician, had written a superior PhD thesis, and he wanted to have clearly a university career. But at those times, it was required that he had habilitation before that. Nowadays, still some people get habilitation, but it's no longer strictly required for becoming a professor, but it was then required. And you had to do 2 things to get habilitation. First, you had to submit a thesis, another thesis in your PhD thesis, which Riemann beautifully and impressively did. And then you had to give a public lecture on the topic. And for that, you had to submit 3 possible topics to a committee. and the committee then would choose one of them, and typically it would choose the first topic. So Riemann gave the first 2 topics from his current research and then didn't really know what to do about the third one. So he had been thinking about some aspect of natural philosophy and physics, connecting physics with mathematics. So he just said, I could, as a third topic, I could speak about the foundations of geometry, and he did not expect at all that this would be chosen. But then, in the committee, there was Gauss. And Gauss said, I want to hear the third topic. And that put Riemann into some difficulties, because within a few weeks, he had to prepare a lecture on a topic that so far he had not really intensively worked on. He had perhaps been thinking about it, but not really so seriously. So he had to fulfill that in a couple of weeks. And the talk was not to a mathematical audience, it was to be delivered to the Faculty of Philosophy, because in those days, universities had 4 faculties. The traditional one, law, medicine, and theology, with clearly defined topics, and all the rest was in the Faculty of Philosophy. There was the humanities, history, philosophy, and all the sciences were in a single faculty. And for habilitation, you had to demonstrate your ability in lecturing to that large audience. And so Riemann had a twofold challenge. First of all, to present a work on a topic that was even new for him, and secondly, to make it at least to some degree understandable. I don't know to what degree he succeeded in that, to a general audience of professors from the philosophy of faculty. And in fact, he beautifully succeeded, impressively, and that was one of the highlights of the history of mathematics, that in this lecture, it's called über die Hypothesen, welche der Geometrie zugrunde liegen, on the hypotheses which are at the basis of geometry, and he founded a new subject, Riemannian geometry. And so let me explain a little about that. First of all, he introduced the abstract concept of a manifold of arbitrary dimension. So far, before that, one had only looked at curves and surfaces. But Riemann came up with a general concept, and then he said, this is just a qualitative notion, and metric relation is something additional, which was also novel, because clearly if you had a surface in 3 space, which were the only examples that one was looking at, they naturally had a metric inherited from the ambient Euclidean space. Yeah, and so the things were not so clearly separated. But Riemann achieved this conceptual separation, the qualitative notion of a manifold and the quantitative notion of a metric tensor. And a metric tensor just is, in our modern terminology, a scalar product, Euclidean product on every tangent space. So if you have 2 tangent vectors at a point, we can multiply them with the help of the metric tensor here and get this product. And in fact, even though things depend on local coordinates, the representation of the metric tensor and the tangent vectors depend on the local coordinates, they satisfy certain transformation rules. This one is a scalar quantity which is invariant under coordinate transformations. So in other coordinates, the tangent vectors look different, because then you have to transform these tangent vectors here according to the chain rules of calculus, and then the coefficients become different. Likewise, you have to change the coefficients here also change, but they transform in such a way, in opposite ways, so that this expression here remains invariant. And this is the principle of covariance that is fundamental for Einstein's theory of general relativity. I will briefly mention that in a moment. So it tells us that we should look for intrinsic properties that do not depend on the representation, independent of the choice of coordinates that we are taking. Now, but when we have this metric tensor here, this is not invariant. So we want to, nevertheless, we want to have invariance of the metric tensor. Of course, we can evaluate it on tangent vectors, but the tangent vectors also change, and so that doesn't really tell us much. Yeah, we want to have invariance of the metric. And for that purpose, Riemann made a fundamental discovery. He developed this quantity which looks a little complicated. Essentially, it's constructed from second and first derivatives of the metric tensor. First of all, you take here first derivatives of the metric tensor, and then you contract it with the inverse metric tensor. I use the summation convention here. If you have an index that occurs twice in a product, like the L here, that is to be summed over the range of indices. That is just the convention called the Einstein summation convention. And so then here we have these quantities that are constructed from first order derivatives of the metric tensor, and in particular here you have then further derivatives, so altogether we get second derivatives of the metric tensor. And these are quantities that look a little weird and strange and forbidding, but from that you can extract the sectional curvatures, and these then become the important invariants of a Riemannian manifold. You can look at my textbook here if you want to have more details, and I've also edited Riemann's work with an extensive commentary. Anyway, but for the moment we do not need curvature, we only need the concept of a Riemannian metric. Curvatures will come back a little later. But Riemann's theorem said from the curvature tensor you can construct a full set of invariants that determine the metric completely. You can construct scalar invariants, the sectional curvatures, the right number of them in order to determine the metric locally completely. That is one of the fundamental theorems in the history of mathematics. Yeah, but for the moment we just need less. We have a point in a Riemannian manifold that later on would take the role of the center of our star graphs, and for other points in the vicinity we can record the distance from that point and the angles that the shortest geodesic from P to Q makes with at that reference point P, and then we get coordinates like the Euclidean polar coordinates. And these manifolds then exhibit what the manifold locally looks like from the perspective of the point P. But of course this does not work globally on a manifold, because in general the shortest geodesics from P to more distant points, to a more distant point in M, need not be unique. So this is just a local representation. Like the Euclidean polar coordinates of course can be defined globally, but on a general Riemannian manifold you can do that only locally. So therefore analogously in our metric space here, from a point X, we take its k nearest neighbors, we rank them according to their distance, and we consider the star graph with X at its central vertex and the edges of a length that records the distance from X to those neighbors Xj. So that is what we're doing here. It's a very simple construction, of course inspired by Riemann's normal coordinates. But now, as I already said, for computation reasons we will modify them as a local metric in order to bring out the local structure. So now we have some formulas here. They're not really difficult. So first we already have the distance from X to its k nearest neighbors. We normalize it. We subtract some number and we divide some number. Of course the distance from a point to itself should be 0. Then the distance between two of these neighbors should somehow be a sum of the distances from the center, but it turns out that it would be useful to have the factor 1 over square root of 2. Originally we worked just with the factor 1, but when I presented that at the talk at Harvard with Michael Friedman in the audience, he suggested maybe to have the factor 1 over square root of 2, which would record independent Euclidean directions. Yeah, that would just be the case if the points of the xj's would point away from X into orthogonal Euclidean directions, and you would get that factor here. And then for all other points we just put the distance equal to infinity. So currently, from the star graph, from the perspective of x, we don't really see the other points. They're all infinitely away. So now we have to justify the choices. So in UMAP, this becomes different. They just also put equal to infinity here, but that has some disadvantages. So now we need to explain the choice of rho x here, what we subtract, and sigma x by which we divide. But first of all, we are now in a category that is a little more general than a metric space, that is so-called Ubermetric space. The term was coined by David Spivak, a category theorist. I asked him, but he didn't really explain to me the reason why he chose that. And anyway, so this is an Ubermetric space. So we still require that it is non-negative, yeah, and that the distance of a point to itself is 0. But we do not require that distant points have positive distance. Different points have positive distance, should still be symmetric and should satisfy the triangle inequality, but the value could also be infinite. Yeah, it could be 0 for different points, but it could also be infinite. So both are possible. So now we choose rho of x. That is just the distance from the closest of the neighbors here. So the closest of the neighbors then just has, in that modified metric, distance 0 from the center point. And sigma x just is a normalization factor. Anyway, maybe let me explain a little more about rho of x. That eases the curse of dimension, because if you're in a very high dimensional space, and if you randomly take points in the ball, then they're all typically close to the boundary. Yeah? They're all typically in some outer shell near the boundary in high dimensions. Yeah? And so the interior neighborhood of the point is empty, and so that is, of course, not so good for doing analysis in high dimensional space. You're wasting something. Yeah? And so therefore, you subtract the distance from the closest point here to have them in a better range. And sigma x achieves some normalization. So a kind of local conformal change to respond to varying densities. Yeah, so in some regions the points may be very close to each other, then you make the distances a little larger, and in some points, in some regions the points may typically be very far away from each other, and then you want to make the distances a little shorter in order to get some uniformity. So therefore, now the closest point has distance 0, and if we divide by the distance from the largest point, then all distances are between 0 and 1. So we have some normalization. Yeah, so all the local neighborhoods are treated in the same way. And everything that is not among the nearest neighbors here has infinite distance. Yeah, and all the other points have infinite distance from each other. We just don't see them at the moment. We just look at the local situation. Now we have these star graphs centered at the sample points, connected with k nearest neighbors. But now, if you have 2 points x and y that are among the close neighbors of each other, then the distance from x to y in the star graph from x may be different from the distance from y to x in the star graph centered at y. So they're no longer compatible to each other, and some other weights are even infinite. So now we have the local situation, we have normalized the local situation, but somehow we want to put things together again. Yeah? How can we possibly do that without somehow losing what we have achieved by the local normalizations? Well, of course, you can ask, why don't we just connect points and don't worry about the local normalizations? And maybe we just connect 2 points when at least one of them is among the k nearest neighbors of the other. But some schemes do that, but they have these disadvantages. And it turns out that by doing the local modification first, we get better results. Okay, now again the question is what to do with these local star graphs, how to recombine them into a global structure. And as I said, as a result of this local modification, the same 2 points now may have different distances in different stars. It may even be that y is among the k nearest neighbors of x, but x need not be among the k nearest neighbors of y. And so in one of the star graphs the distance would be infinite and in the other it would be finite. How can we possibly handle that? Well, in metric geometry it is not so clear how to merge different distances in such a way that we still preserve basic properties like the triangle inequality, but there are schemes in another domain, namely when we merge probabilities. And so that I will explain now. And so that in order to get that, we convert our metric graphs into what has been called fuzzy graphs that we can then merge. That means the following. So in a fuzzy graph, the edges have certain probabilities or membership strengths of being present. And this principle is pretty simple. The longer the edge is, the smaller its probability of being present. If it has length 0, then it is present with probability 1, yeah, like the distance between a point and its closest neighbor. So we always want to have that. If the length is infinite, then it's just present with probability 0, certain absence. Okay, so here's again the metric here. So the closest neighbor is distance 0 by this modification, by this taking this difference here. So in the fuzzy graph, it is there with probability 1, whereas other points have infinite distance and they are not seen from the center, and so therefore they have probability 0 of being there in the star graph. So the edge weights have become probabilities, and we have so-called fuzzy graphs. Now we want to use schemes to combine these different probabilities defined on the same edge. So here is a definition that already was developed, I think, in the 1950s by Charlemagne, who also played an important role in generalizing Riemannian geometry. I will come to that in a moment, and these two things are not unconnected. So we want to match probabilities. The probabilities are numbers between 0 and 1. There's one probability here, another probability here, possibly on the same edge, and we want to get some kind of joint probability. And the scheme that achieves that is called a T-conorm. So first of all, it should be symmetric. It should not depend on the order here. It should be associative. That is, when we iterate that, it should again not depend on the order in which we merge the probabilities. And it should have some boundedness from below. If one of the probabilities is 0 and the other one is A, then the resulting probability should be A, some normalization. And furthermore, we should have some monotonicity. If the two probabilities here are larger, then also the resulting merge probability should be larger. As a small exercise, if one of the probabilities is 1, then the resulting probability should also be 1. Well, by 3 we have the probability of 1 and 0 is 1 already, and then we just use the monotonicity and the symmetry, so that is also has to be 1. That is simple. Yeah? So if one of the probabilities is 1, then the resulting probability should also be 1. If one of the probabilities is 0, then the resulting probability should be equal to the other one. So one example is just we take the maximum of the two probabilities, but there are other schemes. Now, then when we have a T conorm, we can merge our fuzzy graphs in a symmetric and associative manner. Yeah, we just merge all the edge probabilities with the help of a T conorm, and this will not depend on the order in which we take our star graphs. Then we get a global structure, and since one of them is always finite for every edge is contained in some star graph with a finite probability, then we get finite probabilities for all the edges. We can then also translate that with a maximum T conorm into some direct metric relation. Maybe I don't go into the details here, but with other T conorms it's not so clear how to do it in a metric way. And in fact, now we have some choice. So the procedure that we do is not completely canonical, and that is important. We have some choices. We can choose not only the number k of the nearest neighbors, we can also choose the T conorm that we work with, and then experiment on some data sets that we already know, which one works best, and then apply that to the data set at hand that we do not understand yet. So now, again, the scheme. We have samples from our metric data set. We construct star graphs centered at the xi with the Uber matrix that we have. We assign distance equal to infinity to points unless they are both among xi and its k nearest neighbors. And these metrics are normalized to adjust for non-uniform distribution of the samples and to handle the curse of dimensionality, as I had explained. Then the second step is we merge these local star graphs by converting them into fuzzy graphs and use a T conorm for combining the probabilities. And then we use an old algorithm from the 1950s already, the Dijkstra algorithm, to compute the distance function on the resulting global graph. That is not completely trivial, and that requires some time. And we approximate then that graph by a two-dimensional graph as well as possible by minimizing some objective function, the difference on the original graph here and the difference on the projective graph. You can take another objective function or so, that we take the square here is maybe not the most important step, but then we try to find a two-dimensional graph, a graph that we can represent in 2 dimensions in such a way that our data are best represented. So here are some examples. So these are the original data on a hemisphere, and the data are a little denser here. So here is our two-dimensional projection. Here are other ones. So one that doesn't do the local normalization, that of course has a dense spot here, and then the method of choice, UMAP here, that the biologists use doesn't really do so well. But in our scheme, we uniformize it. Yeah? So we have a more uniform representation here. Here are some other ones with different T conorms, how that is achieved. So you can experiment a little with your choices in order to see which one works best. And you can also ask what is the best number of neighbors, and again you can choose the different T conorms and so on. So you have some choices in the method, and here again is the original example here, and so that is how the method that I just described represents this configuration here. And here are 2 other methods. You have seen the picture already at the beginning of the talk, but here it is again. So that is what really comes out if you do the local normalization and then try to spread it out in 2 dimensions. Here are some other examples. You have a so-called Swiss roll here. You have a torus here, and so then you see different representations. And so since this is uniform, a method that doesn't do these choices may look even better. Yeah, but That is not a typical case. Here are some biological data sets. So these are protein chains, and protein chains have complicated configurations in space. So biologists call them knotted. Of course, it's a chain, so you can mathematically easily unknot them, but nevertheless it looks like a knot. And then you have these different proteins here, and you want to separate them into clusters, and that is then in the end what you show to the biologist, and ideally say, aha, now we understand our data. Here are some other schemes, other coloring code in order to emphasize the two different clusters here. One cluster here, and somehow a side chain over here. Now, we have seen methods that were relatively simple, and we have applied mathematical concepts to create and improve machine learning algorithms. But if you look at that as mathematicians, this also can inspire new mathematics. And in the remaining few minutes, I would like to show you a bit about that. So now I really come back to the important geometric concept, namely curvature, which I had advertised earlier, but which didn't really appear so far. Again, we need to recall some history. I told you the history already in the beginning, but again, to emphasize Riemann's discovery, the sectional curvatures, that is the Riemannian curvatures evaluated on two-dimensional tangent planes, determine the metric of a Riemannian manifold locally completely. If all curvatures are 0, the manifold is flat, that is, it is like Euclidean space. Then you have particular spaces where the sectional curvature is constant at all points and in all directions. For positive curvature, you just have spheres or their quotients, and for negative curvature, you have hyperbolic spaces or their quotients. And these are the basic model spaces of geometry. And to recall the history of geometry, these constant curvature spaces serve as comparison spaces in geometry. And so that is what geometric research was mostly about in the second half of the 20th century in particular. If your curvature of your space lies between two constants, lambda and mu, then the geometry of this space somehow lies between the geometry of the space of these curvature bounds. So between the space of the curvature lambda, the lower bound, and the space of curvature mu, the upper bound. And in particular, when the curvature is less or equal to 0, we can compare the geometry of space of curvature less or equal to 0 with that of Euclidean spaces. And so that is what in negative curvature the situation looks like. You have 3 points, and you connect them by shortest curves. You get a geodesic triangle, and in negative curvature, that is typically curved inward. That is what it looks like. And when the curvature goes to minus infinity, it becomes more and more curved inward and converges to what is called a tripod. You will see a picture of a tripod in a moment. And in fact, now we have a local property that is characteristic for negative curvature. Recall that the curvature tensor was defined in terms of second derivatives of the metric tensor. You needed calculus, and had an infinitesimal property. Here we just have local properties which just give some geometric relations. So let me explain that a little. So this was the development started again by Karl Menger, then by Abraham Wald, who subsequently became an important statistician, but sadly died in an airplane crash in India in 1950, and then Herbert Busemann in the Soviet Union, in the United States, and Alexander Alexandrov in the former Soviet Union took this up, and Alexandrov and his school developed the most important such geometry, and his idea was just the following. If we have 3 points in our space with the distances between them, and when we construct a comparison triangle in the Euclidean plane, So the distance between x1 and x3 is the same as the distance between x1 bar and x3 bar in the Euclidean plane, and so on, also for the others. Then the space has non-positive curvature if and only if the following condition holds. You take one point, let's say x3, and connect it with a midpoint or some point on the geodesic joining the two other points. Yeah? And then we do the same here in the comparison triangle, and then the Alexandrov condition says that this length here is less or equal than the corresponding Euclidean length. Then you have non-positive curvature. You can also do comparisons with other constant curvature space, also from above and so on, but that is the principle here. It's a very nice local principle, but it has very powerful applications. But still, that is not really what we need in data analysis. Our spaces are discrete, and so therefore we don't have geodesic connections between data points. So therefore we still need a more general concept, which I have developed with my collaborator Parvane Yoharinath. And so here's a basic question: how to distinguish a tripod from a triangle? Yeah? So we have 3 points here, mutually connected. Here we are also 3 points mutually connected, and so that these are just our spaces. So both of them are one-dimensional. Of course, you see that they're different, but how can we quantify that? Well, first of all, when we assume that the distances between any two distinct points are 2r, just for the sake of simplicity, and then we take the balls of radius r, that is, capture all points that have distance less or equal to r from one of the 3 points, they intersect pairwise. So here's the ball around x1 and the ball around x3 intersect here. Here's a ball around x1 and the ball around x3 intersect here. So that is the same. But of course you notice some difference. In the tripods they all have a triple intersection. They all intersect in the same point. Yeah? Whereas in the triangle, in order to get a triple intersection, you have to go to twice the radius. Yeah? Only if you take the radius 2r of the balls, and of course the ball around x1 contains both x2 and x3. Yeah? And likewise the other 2 balls contain all 3 points, and then we get a triple intersection. So that is a decisive difference here. So in general, for general metric space, some completeness or so is assumed. You find some lambda between 1 and 2 in order to get a triple intersection when you have pairwise intersections. Yeah? And 1 is an extreme case. Of course, you cannot make the ball smaller, the radius smaller than r, because that is already needed to get a pairwise intersection. And under some mild and obvious assumptions, you don't have to make the balls larger than 2r in order to get a triple intersection. And for every space, the number to get that is between 1 and 2. And so that quantifies the curvature. The smaller lambda, the more negative the curvature is. So here, the 3 Euclidean balls intersect pairwise, but they don't have a triple intersection. But now we can show that this connects very well with Riemannian geometry, Riemannian manifold. If we happen to be on a Riemannian manifold, it has non-positive curvature in our sense, if and only if it has non-positive sectional curvature in Riemann sense. So that is the theorem here. But let's look again at now how this applies in data analysis. We have topological data analysis. I mentioned that already. And we have a metric family of points, and we have balls. And then we construct the check complex. Whenever we have q plus 1 balls with a non-trivial intersection, then we have a q-dimensional simplex. Yeah? So the points or balls themselves are the vertices. We connect 2 by an edge. If they have a pairwise intersection, we connect 3 of them in a triangle if there's a triple intersection. But here, of course, we don't have a triple intersection. The simplicial complex here is just this unfilled triangle. Of course, if we enlarge them a little, we get a triple intersection. But of course, although from the point of topology, here the triangle is not filled, so we get a hole, and so therefore we have non-trivial one-dimensional homology. Now, in topological data analysis, it's difficult to compute the check complex, so people do something simpler. They compute the Vietors-Rips complex, and they already fill the triangle if you have pairwise intersections. So here, in the Vietors-Rips complex, they would already fill the triangle. Now, obviously, there's some difference, but our question then is, how much do we have to enlarge the balls to get triple intersection? So what is the difference between the check and the Vietors-Rips complex? And so we can understand now this topological data analysis from our geometric perspective. And we can also use it to evaluate the quality of a low-dimensional representation of a high-dimensional data set. That is, we can then ask, how well are these curvatures preserved, these intersection properties? Yeah, in general, of course, you can do anything. You have a two-dimensional representation, so how do you evaluate it? If it looks nice, as in our mammut example, or if it's appealing to the biologist, but of course you want to have a mathematical criterion. And so therefore we propose our curvatures. And our algorithm does pretty well. And of course, these are large-scale properties, so we don't do it locally. So, but as for the last slide, we just look at a traffic network. So when you have a traffic network, how do we qualitatively analyze it? It could be like the French railway network, where everything is connected to a central focus, namely essentially all the fast-speed railway lines in Paris start and end in France, start and end at Paris. So this is a particular type of a network. The opposite network would be a circular network, where all the destinations are arranged on a circle that is rarely achieved. Both have certain advantages. So the French railway system makes the average length, makes the length of the total network relatively small, but of course it runs the risk of congestion if you just had one central train station. I mean, one doesn't have that in Paris, there are several train stations, but if you just had a single train station, then there would be a risk of congestion. Yeah? The ring structure avoids that. There's very little risk of congestion, but of course you need more lines and it's not efficient in terms of network design. So you can balance these, and when you have an empirical network, then you can check all the curvatures in order to see whether it's closer to the star pattern or whether it's closer to the circular pattern or what else you might see. Okay, so that is the end of my presentation here. I think I have more or less respected the time limit that was given to me, and of course I will be happy to answer any questions that you might have.